Multivariable calculus, picking back up in 16.3, our first day. This theorem that we have at the top of the page here for number 5 in the box, it's really saying the key question is, how do we know when a vector field is conservative? If f is our vector field and it's a function pi with a plus qj, p and q then are continuous first order derivatives. Let's assume that you do have a conservative vector field. That means that p is going to be from the gradient, the partial derivative of f with respect to x, and q would be the partial derivative of f with respect to y. Remember how gradients work. Gradients are saying that you have the partial derivative of f with respect to x for your I component, the partial derivative of f with respect to y for your j component, and that's essentially what capital F, that conservative vector field, is saying. Well, what you can see is, going back from a couple of chapters, we had Clairaut's theorem that said if you take the next derivative, a second derivative, but switching the variable, if you took the derivative of f now with respect to y, take p with respect to y. First we took the derivative with respect to x, now we take the derivative with respect to y. Do the same thing with q. Originally q was the derivative of f with respect to y, but now we'll take a second derivative of that, but this time with respect to x. Clairaut's theorem says that those two second derivatives would have to be equal. So what we're seeing here is, if we have this conservative vector field, then of course from what we saw before, the partial derivative of p with respect to y should equal the partial derivative of q with respect to x. Now, with a contrapositive, in logic we'd say if p implies q, the contrapositive would say not q, the negation of q, would imply the negation of p. So this means if we had our conclusion here, if we negate that, if our partial derivatives are not equal, if the partial derivative of p with respect to y is not equal to the partial derivative of q with respect to x, that means we're negating our premise. We're saying that f is not conservative. So if these partial derivatives aren't equal, we can say f is not conservative. This right here, though, bullet point number 6, or this box number 6, says really the converse is also going to be true, which is amazing. We're going to say if those partial derivatives, if the partial derivative of p with respect to y does equal the partial derivative of q with respect to x, throughout our domain D, that region D, then we have a conservative vector field. If we have a conservative vector field, we can use our fundamental theorem. So some problems that you're going to have are going to be nothing more than just determining if your function f is conservative. So let's look at letter A. Here's your p, here's your q, and I'm saying p is equal to x minus y, and q would equal x minus 2. Well, p was the partial derivative of that gradient function f with respect to x, so we're going to now take a second derivative, this time partial derivative of p with respect to y. And the derivative of x with respect to y is 0, the derivative of negative y is negative 1. We're going to come over here and take our partial derivative of q with respect to x. And as we do that, the derivative of x is 1. These are not equal. What does that mean? Well, it means that f, our vector function that's determining the vector field, is not conservative. What does that mean? We can't use that shortcut that we did on the front page. For B, we've got a different vector field that's going to have P equaling 3 plus 2xy, and Q is going to be x squared minus 3y squared. Well, the partial derivative of P with respect to y is going to be 2x. The partial derivative of Q with respect to x would be 2x. These two things are equal. So we can now say our vector field F is conservative. What does it mean for a vector field to be conservative? That means that that vector field is equal to the gradient of some function f. And that is really where we're going with example 3. Example 3 is now going to follow up. We're going to deal with this exact problem that we just did for part B. And we're going to say, let's say that we've got our vector field, and we already know that it's a conservative vector field. Could we find the function f such that capital F is equal to the gradient of f? So what's going to happen is, if f is really equal to the gradient of some function f, what was the gradient of f? Well, it was the partial derivative of little f with respect to x, partial derivative of f with respect to y. But f, of course, is the function p comma q in vector form. So what are we really seeing? We're seeing that p is the partial derivative with respect to x. That's the 3 plus 2xy. We're going to see that our q is our partial derivative of f with respect to y. So now that we can say really that p and q are really partial derivatives of some function f, the bigger question is, could we find that function f? Because if we could find it, we very well could use our shortcuts that we've talked about. Well, here's what's going on. As we're looking here, we can say, well, I'd like to go backwards. I'd like to find f. The partial derivative was the derivative. To go backwards to f, we're going to have to take antiderivatives, of course, with respect to x. The antiderivative of 3 is a 3x. The antiderivative of a 2xy, remember y is just thought to be a constant, we'd get x squared y. And then we could have a constant, but that constant, I'm not going to write just as a numeric value like a plus c. We're going to say, look, y was filling in for constants before. And we could say it's some function of y, g of y. Maybe there are y's in that function right there. Maybe there are some numbers mixed in with it. Maybe it's something like 7y minus 8 or something like that. But we're much better off right now. We can say, wow, we're closer to finding the function little f. But now I could also take a derivative of f with respect to y, because I have information about that from q. Take your derivative of 3x with respect to y, that's 0. Take your derivative of x squared y with respect to y, and you'll just have x squared. And take your derivative of g of y, and you'll have g prime of y. Now, you might wonder why we did that. The answer is because if we look above, we can see, hey, we had some information about the partial derivative of f with respect to y. We know what that's equal to. So we're going to take that and say, hey, you know what? We can now say that these two partial derivatives with respect to y have to be equal. Well, I hope you can see very quickly we can subtract an x squared from both sides. And then g prime of y, to find just g of y, we'll take our antiderivative with respect to y. Negative 3y squared, bump that up to a 3 and divide, you get negative y cubed. But now I'm going to put a plus k in there. I'm putting in a plus k because we already assumed up here for f that g of y was strictly a function of y. Y's could be in it, or there could be other fixed numbers in it. What do we really know now? F is 3x plus x squared y, and then our g of y is our minus y cubed plus k. That's our function. I don't know what our constant is. We can certainly find it if we had more information. As you might realize, there could be infinitely many answers for this. Well, we know that our vector field is conservative, and now we can investigate part B. Part B says, hey, could you find this line integral where r is defined parametrically on this curve, and it has these boundaries. And what's going to be so neat is we could say, well, ultimately, this is a line integral of a gradient of f. That's what capital F really is. And, what we do from here is we can say it's going to be f of our ending point. It's just a function of x and y. Minus f of our first point, our initial point. And we have our function. All we have to do is plug in our beginning and our ending point. To do that, please realize that's why they gave us r of t. If I were to let t equal 0, our first point, remember that r of t, we could rewrite it as a vector with brackets. We'd say that's e to the t sine of t, comma, e to the t cosine of t. And without too much work, when we plug in t equals 0, we could see we'd get a point, e to the 0 sine of 0, e to the 0 cosine of 0. And we know that the sine of 0 is 0, and the cosine of 0 is actually a 1, and so is e to the 0. So we have that as our starting point. But of course, likewise, if we came over here and if we said, well, what about plugging in a pi? Well, if we plugged in a pi, we'd get e to the pi sine of pi, and we'd have e to the pi cosine of pi. And what's this point? Our ending point is going to be, well, sine of pi is 0. We'd still have a 0. But the cosine of pi is negative 1, so we'd get a negative e to the pi. So this is really what's happening. We're going to be saying go to your ending point minus plugging in your beginning point. And we now know the function that we're talking about. It's this function that we have right here. So let's do that real quickly. Plugging in our first point, plugging in an x value of 0 and a y value of negative e to the pi, we can say, well, that's 3 times 0 plus, well, that's 0 squared times a negative e to the pi minus, here's our negative e to the pi, cube that, and then we'll say plus k. Well, then we're going to say, you know what, now we're going to have to plug in our 0, 1. And when we do that, we'll get 3 times 0 plus 0 squared times 1 minus 1 cubed plus k. Well, it only takes a moment to realize that anything multiplied to a 0 is going to wipe out. And that leaves us with, let's see here, this is a negative 1 to the third, that's negative 1, and a negative in front of it makes it a positive, and that's going to leave us with an e to the 3 pi, right? So I have that e to the 3 pi here, plus k, and here as we distribute this negative 1, we're going to make that a plus 1, and then we'll have a minus k. You can see we'd have e to the 3 pi plus 1. And that's going to be our line integral.